Hi there, welcome back to Think Tank Online Learning. In this video, we're going to look on thermodynamics. So given a question, the properties of a system during a reversible constant pressure non-flow. Okay, so as you can see, this is a constant pressure. That means it's an isobaric process, right? The pressure is not going to change, it's going to be the same, it's constant. So given that P is equal to 1.6 bar, and you should be able to change bar to Pascal or to kilopascal. Change from V1, we're given the volume, given T1, so this is initial temperature and initial volume, to V2 and T2, so these are the final temperatures. The specific heat of the fluid is given by, so as you can see, the specific is a direct relationship with the temperature. So this is the specific heat and temperature relationship. It's 1.5 plus 75 over T plus 45. These are the units, which are kilojoules per kg degree Celsius. And after that, our temperature is degrees Celsius, so there's no need to change it to kelvins. So what we want to do, want to determine for each kilogram the heat added, work done, change in internal energy, and change in enthalpy. We know that the heat added, we can just calculate it by multiplying the specific heat capacity and the temperature, right? But in this case, you can see that our specific heat is given in terms of T. So what we're going to do, we're just going to integrate, right? We're going to integrate Cp with respect to the temperature, right? So I'm going to write dt. So that is going to give us the specific heat added. Okay, so let's do that. So we're going to write it here. Heat added is going to be the integral. We're going to have our limits. We have the initial and the final temperature. So as you can see, T1 is 20 degrees and T2 is 260 degrees right here. And the specific heat given by the formula 1.5 plus 75 over T plus 45. And this is going to be dt, meaning that we're going to integrate this with respect to temperature. So it's 1.5, just a constant. We're going to add T plus, right here it's 75 over T plus 45. So you're going to use integration by recognition. So it's going to be 75. We're going to put the natural log of T plus 45, right, in brackets. And we still have our limits, 20 to 260. Okay, so now by saying upper limit minus lower limit, we're going to have 1.5 times 260. We're going to add 75 lean and still 260 plus 45. We're going to subtract the lower bound, and the lower bound is going to be, we're not plugging 20 degrees here. It's going to be 1.5 times 20 plus 75, natural log of 20 plus 45. And if we do this, we're going to get 475.94, and I'm going to express my answers in kilojoules. So it's going to be kilojoule per kg. Okay, so that is going to be the heat added. And now we're going to move to the next question, which is going to be the work done. Okay, so on the work done, we know that the work done is given by the integral of pressure with respect to the volume. So that's what we're going to integrate. So let's integrate. So just going to have P, and we're going to have V, and we have V1 and V2, these upper bounds and lower bound. So now let's do that. Our pressure is 1.6 bar. I'm going to change bar to Pascal, or can change it to kilopascal. So I'm going to write times 10 to the power 2. That's going to be kilopascal times V1, 0.55 minus 0.3. And I'm going to write kilo right here. So kilojoules is going to break down. Okay, and if we multiply here, what are we going to get? We're going to get 40 kilojoules, right? So that question is the change in internal energy. And what do we know? We know that the heat added is going to be equal to work done plus the internal energy, right? And we have the heat added and also have the work done. So if we make use of the formula, we're going to see that U is going to be Q minus W. And this one is going to be, we said it's 475.94 from 1 right here, kilojoules, minus, right here is going to be 40 kilojoules. And if we do that, what we're going to get? We're going to get 435.94 kilojoules per kg. That is going to be the answer. Okay, change in enthalpy, that's going to be the last question. But as you can see, this is a non-flow process. So if the process is non-flow, that means change in enthalpy is going to be the heat added in the system, right? So it's going to be Q, and this one is equal to 475.94 kilojoules per kg, right? But just in case you don't know if it is a non-flow process or event rate, as you can see, we are told that this one is non-flow process, but let's say you don't want to do this method, you can just use the enthalpy method. So you know that M stands for mass, is equal to U plus pressure times volume. Okay, so mass is per kg, we know that. So what is U? So use the internal energy, it's going to be 435.94, right, kilojoules per kg. Now going to add pressure. What is pressure? Which is constant, 1.6 times 10 to the power 2, and we're going to multiply the volume, but the volume with initial and final. So I'm going to say 0.55 minus 0.3, and our still are going to get 475.94 kilojoules per kg.